Okay, so I'm Andrea Barisani. I'm the founder of a company called InversePath, which you might or you might have not heard of. I'm gonna talk to you here, very honored to be in this very beautiful venue, about our latest open hardware project, which is the USB Armory. So how many of you have heard of the USB Armory? Please raise your hand. Okay, so there's a fair number of people that doesn't know anything about it, which is great, so that I can tour you about this project. So what is the USB Armory? The USB Armory is an open source computer which has been designed in a tiny form factor, and specifically the form factor of a USB stick. So why are we doing this? So as a company, every 2 years we try to publish a research which has to do not only with software, but as well as hardware, and of course, in the point of view of security. We talk about hacking cars for the first time in 2007. Then we did side channel attacks over the power line, attacks on credit cards and so on. And 2 years ago, we wanted to, for a change, to make a talk where we create something and build something rather than break something. And we wanted to take our expertise into embedded systems auditing into actually creating one. And the reason why the USB Armory was created in the first place was for personal security applications, because the first thought that we had was we need something, we want something that can provide us encrypted storage, but not, with some military-grade encryption USB drive, which you really don't know what it's actually doing, and that most of the times when we do audits on these kind of devices, their security, especially if you have physical possession of the device, can be broken or bypassed very, very easily. So the first idea was, why don't we do an open hardware device which can provide enhanced mass storage? So instead of just providing a standard USB drive, it would also maybe, filter, scan, and encrypt, maybe with GPG or something, all of the contents before actually being saved on a micro SD card. And then we thought, but mass storage, okay, it's a driver which is very well understood by all computers, but why don't we do a device which can provide a richer interface than just, copying files to it? So this way we could leverage a more complex authentication and more secure methods. So why don't we just provide a device which supports TCP/IP over USB using the standard drivers that are there for emulating an Ethernet device over USB. And then maybe we can expose a richer application using a web server or something. And once this transition was clearly in our minds, then we quickly realized that we need something a little more powerful than just a microcontroller on such a device. And we thought, but if we have something more powerful and also something where you can customize the code that runs on it, we can do some crazy and exotic things which you don't find in devices nowadays, such as if I copy a certain file, if I input a certain password, maybe we have a fail-safe word detected, maybe the device will just wipe itself, so some data self-destruct or functionality like that. And then we took it further and we said, but if we have TCP/IP connectivity to this device, then we can SSH to it with credentials that we don't care too much about, or maybe one-time credentials, and then you can have your keys there, and if you route it, you can use it on SSH proxy. Or, of course, you can use it as a password manager. All of these kind of ideas quickly came out as something that we could implement on such a generic device, authentication tokens and so on. And also, more importantly, if you have a device which provides richer functionality where you control the code that runs on it, there's no reason why not only you can authenticate to the device, but also the device can decide to authenticate the host that is being connected to. Since it becomes a full computer that can actively perform tasks as soon as it's plugged into your computer. So, the idea was that you can also have a device that as soon as you plug it in, will communicate to your laptop or host computer, and if the device itself decides that for some reason the host that you're connected to is not the one that it's supposed to talk to, then actions can be taken, if that condition is being detected. So we set some design goals very quickly. So for supporting all of these applications, it needs to be a compact USB-powered device, so no external supply. It needs to plug in directly into a USB port without a cable or something which is fiddly. It must be a little bit future-proof, so it must have a fast CPU and a generous amount of RAM given the form factor and the applications of the device. It must support secure boot, so the code that you're executing on the device, it must be possible to verify that it is the intended code that you want to execute, so that it's signed with your own keys. It must provide standard connectivity over USB, and also, very important for us, the development environment must be familiar, not something which requires, some specific vendor SDK or IDE, code development tools. It must be something where you can easily put code in the same way that you would put it on a server or on your laptop. You can put it on this device, and of course, the design must be open as possible. So one of the first tasks into one of the most important choices that you have to make right away when you design such a device is selecting the correct components, and specifically the system on a chip. So a system on a chip is a CPU which also has a lot of internal peripherals which help you in designing such a device, and also when you want to make it very compact. We selected the formerly Freescale, now NXP IMX53, because we were very familiar with this device, with the security features of this component. It's also used heavily in automotive, which is where we stumble upon it. It's an ARM Cortex A8, which can be clocked up to 1 gigahertz. Almost all datasheets and manuals are public, which is good. No NDA is required. The documentation is actually fairly good, which for hardware, it's always a good thing when it's not super crappy, but it's actually fairly good. It has some security features, which I'm going to mention about later on. Detailed power consumption guide available, which for us was important when developing something that needs to be powered over USB, so the amount of current that you can drain is limited. And there's excellent native support for Android, Debian, Ubuntu, FreeBSD, and so on. And good stock and production guarantee. You don't want to commit to a design only to realize that maybe after 2 years the part is not available anymore, because that sucks a lot. So in this case, they're going to produce this part until, I think, 2021. This device, the system on a chip, has a lot of peripherals. There's a canvas controller, display controllers, 2D and 3D GPU, and our design tries not to power on the blocks that we don't need to be powered on, to reduce power consumption on the device and to simplify the design as much as possible, because we have to cram it in such a tiny space, which is unusual in this kind of designs with these specific components. In terms of hardware security features, we have something called high assurance boot, which is authentication of the initial bootloader, which means secure boot. So in NXP parlance, it is referred to as high assurance boot, but it's really secure boot. We have a security controller, which is a hardware module which can do AES encryption with a device-specific key. And then there are a lot of cryptographic accelerators, which actually, it turns out that if you use them, the overhead in doing DMA to and from the accelerators is actually, it takes more time than doing those computation over in pure CPU. So unless you're having parallel tasks to perform, those are not really useful, and we're not going to cover them. We're just going to cover the first two security features later on. And also, we have a very complete implementation of ARM TrustZone. So ARM TrustZone is a feature which is must be supported both by the CPU core as well as the peripherals that are connected to the system on a chip for separating the execution domains in a non-secure one and a secure one. And the idea is that you can also leverage on functionalities such as a sort of hardware firewalling functionalities, where you can decide to segregate a specific hardware components, let's say the USB controller or the microSD controller, only to one of these two domains. And this allows to have further separation within the device, which it can be useful, and it's certainly a good playground, because one of the things that we see with TrustZone is that the threshold and the learning curve to approach it is always very high, and we also wanted a device where we could do trainings and we could experiment with TrustZone very, fairly easily. I'm not going to go too much into TrustZone. There's a very nice article from the Genode OS project. So Genode OS provides an implementation of TrustZone which is supported, provides support for the USB Armory. And the idea is that you boot a richer OS such as Linux into the normal container, while into the secure container you have a microkernel-based lightweight OS such as Genode OS, which can take over certain functions or certain drivers and exposing virtual drivers to the Linux OS, so that you can do things like encrypting the microSD, but the key remains in the secure domain. So even if your Linux instance is completely compromised and your root on it, you cannot dump the key from memory, because that will be segregated on TrustZone. So if you're interested into this, the Genode OS provides a good example for this on the USB Armory. So And of course, it's open source. Every software we publish for it is open source, but also the hardware layout is as open source as possible. And at the end, it's a very tiny device, as you can see, 65 millimeters by 19 by 6. We have a micro SD card slot, which is where all of the code comes from. So there's no persistence on the device. All of the code which is being executed, other than a very tiny boot ROM, which can be dumped, by the way, which is not something that can be done on most hardware, so you can inspect that at least. All of the code comes from your micro SD card. We have a breakout header for GPIO, serial, I2C, SPI, and so on. And we also have a LED, which, in case you use in TrustZone, can also be used to indicate that the TrustZone code is being executed if you want. That was the original reason for putting it there. And it's now supported by Debian, Ubuntu, Arch Linux ARM, Genode OS again, and it can emulate any USB device. So this device is primarily designed and was primarily designed to be used in device mode. But, you know, and actually after having the first production, we realized that the USB controller on this device is so forgiving that even if the hardware layout was specifically designed for device mode, so we were driving the ID pin in a certain state that usually it's associated to device mode, we can also have it to host mode. So this was actually a picture from the first test that we did, where with a very crude breadboard gender converter, we converted the male USB form factor to a female USB form factor, and we attach it to a power USB hub. We plug a Wi-Fi card, a USB keyboard, USB mouse, a USB displays, and then we could actually use the device entirely on its own. So because we thought this could be also nice for certain applications, just to have it on its own, we designed a very inexpensive and cheap host adapter, which just changes the gender of the USB Armory. There's one configuration flag in the Linux kernel that you flip, and then you can use it completely standalone. So in this example, there's a Wi-Fi adapter on the left. You just feed power back in, and then you can use it as your own, you know, access point or whatever you want. So this was also it was nice to see that we had the capability of doing this, but after, you know, we produced the device. So we didn't think it before, but it's just something that we could do it afterwards. And it's because the USB host controller, you know, it actually provides you a lot of freedom, which also, you know, it's also a good thing for testing, as I will mention later on. So for developing this kind of hardware being so tiny, typically the components that you use for this kind of design are BGA components. So BGA is ball grid array, which means that you have a packaging factor where all of your contacts are below the actual component. And it's actually, you know, it's fairly difficult to solder and desolder this on your own. And so prototyping these kind of devices is always quite a challenge. So we thought to be clever at first, and we thought, okay, let's create a breakout board where without having to solder anything. So we bought this. This is a very nice but expensive socket which allows you to clamp and screw the system on a chip on a socket, which requires no soldering whatsoever. And then you can break out all of the different connections of the system on a chip in order to do some development on it. And we thought it was a good idea at the time. It was a terrible idea, in fact, because the tolerances for the various distances of the components required for powering up the system on a chip in the first place are so high that it's very difficult to create a working power regulator for this device by soldering on your own. So this thing has about 6 or 7 power rails, and we will get, you know, most of them will be stable, but then will be 1 or 2 that will be unstable. So at the end, we realized that in order to do the power components for this device, we actually need an actual PCB. But if you have a PCB for the power component, then you can put the system on a chip on the PCB as well. And if you do that, then you can also put the RAM. And if you do that, you can also put the micro SD. And if you do that, then you have the first prototype. So the first prototype of the device was actually something which is surprisingly close to this final design. So the message here is that if you're doing open hardware, you know, be brave. You know, sometimes if you try to overthink it and over-optimize your development process, you might end up, you know, doing the wrong choice. And actually, in our case, going for the final design from the beginning was actually the right choice. So this was an effort which, maybe we would have saved some money if this would have worked, but certainly didn't save us time, and at the end also didn't save us any money. So this breakout board, which we did, is very fancy. It's like a superstar destroyer. It's something which is expensive, it's big, but it really doesn't work, and it's gonna crash down on a planet or something else. So, it's there in our office. It's very nice. It was a brilliant effort, completely useless. So, lesson learned, but it makes for good pictures. The second challenge was that we wanted the design to be open, but we also wanted the tools to modify and access the design to be open as well. Because if you do an open design and you publish the sources of something which requires a 20,000 euro license, it is open technically, but it's not something which is nice. So we decided to use KiCad or KiCad for this project, which is open source software, which when you want to make such a tiny design, it really, really doesn't help you in achieving your goal. And one of the biggest challenges here was that, so on the right side you have the RAM module, and on the left side you have the system on a chip. And all of the traces that needs to go from the RAM to the system on a chip, they all need to be exactly of the same length, to the third decimal point of a millimeter. And that's because A, you don't want to take any chances. And B, because, if one of them is longer than the other, then you're going to have RAM issues which you cannot simply fix. And at the time, and even now it's not really mature, there was no length trace matching feature into KiCad. So all of this was done completely by hand into matching the length of all of these traces. And normally, when you're breaking out these connections, you can go around the system on a chip from multiple angles. So you can go on the side here, and also you can have a longer distance between the system on a chip and the RAM, which gives you more room to do a lot of zigzags and do the length trace matching. But here we don't have that, because our system on a chip is at exactly the edge of the board on two sides. So this was quite a challenge with this tool. But for the sake of open source, we took the effort of doing this by hand, and at the end it worked. And that was one of our biggest risks, that the RAM would just not work properly. On the other hand, the 3D viewing capabilities of KiCad, sorry, there's a huge fly here, they're really excellent, which they're not really that useful, but at least as an open source tool, this works brilliantly and much better than commercial tools. So there's that. So the schematics can be downloaded, you can modify them, you can access them. So the electrical schematic as well as the PCB layout. So, and it's licensed with a certain license, which has no commercial restriction whatsoever. So it's as open as it gets in terms of hardware design. So this was the alpha prototype, which is the same form factor as the final version, but it has a JTAG connector there, so that in case something would go wrong, we could easily access that port. And it was also designed so that we could cut those two excess surfaces, and it would actually still work, and it would actually represent our final form factor. It turns out, it turns out that the JTAG connection wasn't actually necessary, because our first alpha prototype worked right away. But nonetheless, it was there, and this is now in our office museum. The first board worked right away. And I think, it's kind of amazing that with completely 100% open source tools in, 2 months, you can design from scratch a hardware which is a full computer of that form factor, which is more powerful than a Pentium 2 of a few years ago. I think it's rather cool. But Darth Vader there prefers black much more than green, so we made it black, so they would look even cooler, because, that's the way it's supposed to be. It's supposed to look cool as well. So you can see the different iterations of the boards. That was the alpha prototype. With the betas, what we did, we found out the number of revisions that we could do in one single production. So in a single panel, we could do 7 different versions, and we tried to optimize and lose certain components or replace certain powering methods with components that would not cost 5 euros, but maybe would cost 1 euro, to try to optimize the design as much as we could and to lower the cost. And we found 2 versions that were good for that purposes. One was much more stripped down than the current version, but it was consuming more current, it was draining more current, so it wasn't as effective. So we found the best balance of features, and then we made the final version, which is there. So we basically went through 3 different production runs to find the final production version, and the second one, it was testing 7 different designs at the same time. Okay, so now before covering the software that were on the device, I'm going to talk about the security features of it. So the first and most important one is secure boot. So the system on a chip supports high assurance boot, which allows to fuse your own public keys. So we're not talking about OEM keys that we put or that NXP puts. You can fuse your own public keys, and this is a one-time permanent operation that then are going to be used to verify the authenticity of the bootloader that you're going to execute, which in this case is U-boot. I mean, it can be anything, but U-boot is the one that supports this device. And this activation, unlike a PC, it's not that you can go into the BIOS or something and then you can reset or clear that option. Once you do it, it's there forever, and this is a feature, not a bug. And you can also revoke up 3 keys out of 4. So you can also do nice things like you put 3 legitimate public keys, the 4th is random, and then if you revoke the first 3 ones, you end up with a brick and nobody can ever execute code on it, which it is also something that you can do. So we have published procedure for that, but the way you do it, you go into the bootloader and you fuse the hashes, the combined hashes for the public keys that you have. And now, also this was part of our effort, which I think is interesting. NXP provides a code signing tool which allows you to sign bootloader images, but until very recently, their last version was buggy and they wouldn't publish the previous version which was working. And anyway, an NDA is required to download this tool, which is annoying. Well, it's actually not an NDA, it's an end user license agreement, which is not too bad, but it's annoying to go through that process. So for transparency, we decided to re-implement what these tools are doing as open source software in a way that not only is readable so that you can understand what goes on and how the signature is actually computed, but it also makes it easier for executing as in your environment, and it doesn't require to pull binary blobs from NXP. So we provide guides both in using the NXP tools, which is not trivial, so that's also a useful guide for anybody that uses NXP tools, and we also have the same guide but with our own tools, and everything is on our GitHub repository. And we have 2 tools. One is for the hash generation, which is then fused on the system on a chip, and one is for signing the bootloader. They take your keys and then they produce the output. Now, when you want to maintain a secure chain of trust, secure boot plays a role only in the very first phase. So secure boot provides an anchor between the hardware and the first piece of software that you're going to execute. So in this case, the bootloader. So with secure boot, you fuse your key in the system on a chip, and those are used to verify the bootloader. But then, of course, you want to maintain this chain of trust, because if the bootloader is not going to verify your Linux kernel, for instance, then having secure boot is not really useful. So U-boot supports something called a verified boot, which allows you to embed a public key when you're compiling the bootloader to verify the Linux kernel image that you're going to boot. So, and with this feature, you maintain the chain of trust because your U-boot image has been verified by the hardware, and it is the one that contains the public key which is going to verify your Linux kernel image. This is an example, a successfully booted U-boot image. So no high assurance boot events found. And this is an example of a failed attempt. Now, the example for the failed attempt here is done into verification mode. So verification mode is an intermediate step where you're not locking the feature yet, but you can test it. And the reason why you have this is to test that you have the capability of actually signing images, and then you're not ending up with a brick. And also, when you have a failure in final mode, you're not going to see any output, you're not going to see anything, because the bootloader code is just not going to be executed. So you cannot even get an output saying you the secure boot failed. The CPU will just hang and nothing can happen because no external code will ever be executed. And this is an example of verified boot. This is an output from uboot where it will verify the hashes for the kernel and the device tree blob, which is an external file which provides certain hardware configuration, which are the two pieces of components that are going to need it for booting up your Linux OS. I'm going to explain how this is going to all play it out in the piece of software that we provide for the USB Armory in a second. There's a second feature, a hardware feature on this system on a chip, which is called the SEC v2. This is not a standardized name. Don't be fooled by that. It's an NXP name for a security controller, which is some sort of HSM. So it's a hardware module which is in the system on a chip, which implements 2056-bit AES using a key which is fused in each system on a chip, and it's unique and it can never be read. It can only be used. So you can ask the system on a chip to do encryption or decryption, but you can never ask it to give you the key back. And there are certain hardware properties which protect this key inside the processor. And it is generally used to derive device-specific secrets for full disk encryptions. And more importantly, this key is only unlocked to you if you're secure booting. So if you're not secure booting, there's going to be a standard test key, which is going to be the same for every device, which is going to be used for encryption. So, and the reason for this is that the theory is that you want your own code, which supposedly it is locked down to be secure booted and accessing the decryption and encryption function. Otherwise, anybody can use them. We ported a driver for this, and we created an additional drivers that allows to use this security controller very easily. It's as easy as opening a Carter device. So that's a Ruby example. You set the mode, either encryption or decryption. You set the initialization vector, and then you just spit blobs of data to the device, and you read back blobs which are either going to be encrypted or decrypted depending on the mode which you set. And we have support for this in Interlocked software, which is what I'm going to cover now. So Interlocked is, we created this hardware device, and then we wanted to, create some, reference software that actually shows one of the many ways that you can use it, because of course this is a platform that can be used for many, many purposes. So Interlocked is an open source file encryption frontend which was developed for the USB Armory, but is not limited to being used on the USB Armory. If you have, you can use it on your own laptop if you want to. You can use it on a Raspberry Pi. You can use it on any hardware that you want, as long as it can run Linux and you can execute Go applications, which means any Linux hardware, because you just end up with a static binary, which is just going to work. And the point of Interlocked is to provide a web-accessible file manager which will be a front end for Linux Unified Key System encrypted partitions. And also we wanted to put in some additional cryptographic operations for symmetric and asymmetric operation on stored files. So I'm going to show you a demo of this application, hoping that the demo gods will be kind to me. So I'm going to take my own USB Armory, which it's an enclosure. We also have an enclosure, by the way. And I'm going to show you the various features that this front end has. So, and also what I'm going to show you is that not only we have encryption features for on files, but we also have messaging capability, and I'm going to show you the Signal plugin that we have for it. So what I'm going to do, I'm going to connect to my USB Armory. In this specific instance, so I tested this before, so you're not seeing the pop-up here, but the USB Armory itself is demanding for a very specific client certificate in my browser. So if I don't have that certificate, I cannot talk to it. So this is already one form of authentication which has been happening here. And then I'm presented with, let me zoom a little. I'm presented here with a volume name prompt and a password prompt. So these are going to be my credentials for logging into the USB Armory. Now, what's going to happen is that volume is the actual volume name of an encrypted partition, and the password is one of the multiple passphrases that you can have for an encrypted partition. And if for some reason I don't trust the operating environment that I'm using, if I want, I can tick this box, and the passphrase that I'm going to use is going to be wiped as soon as I'm logged in. So if anybody intercepted the password on my laptop, maybe by doing shoulder surfing, that passphrase is now useless, and you can have more than one. So you can have a one-time password here. as soon as you input your credential, what's happening right now, an encrypted partition got unlocked. And I get this partition accessible with a file manager when I can, I can decide to compress files, I can download files, and I can also upload files if I wanted to. So I can just, if I have a file here, now it got uploaded to the USB Armory. If you're on Windows and you don't have a very minimalistic Windows environment like the one that I have here, you can also drag and drop files directly into this area, and they'll be uploaded. And then you can decide on these files, you can encrypt them. Now, we support 3 different encryption methods. You can have standard symmetric encryption with the passwords that you choose. You can have the same kind of encryption, but being piped through the security coprocessors. So the actual key that is going to be used for encryption is not only your passphrase, but it's also combined with the unique secret which is on the USB Armory itself, which means that you can lock encryption and decryption of that specific file to this specific device. So if I take the microSD card out from this USB Armory and I use it on a different USB Armory, even if you know the passphrase, you won't be able to encrypt and decrypt that file again. And this can also be done for the initial credentials that I use for logging into the encrypted partition if you want. So this is an optional support which you can enable. And also you can do Pgp encryption and decryption. So I have 2 keys here, and now I just encrypted this file with Pgp. Now, the way we have Pgp functionality is not by piping through a GPG binary, but it's actually all using standard native Go libraries, because this is a Go application. So there's no outside dependencies over standard Go libraries except for the optional signal support, which I'm going to show you in a second. And once you have the files here, you can compress them, you can download them, you can delete them, you can do whatever you want. And everything that you see here is living on an encrypted partition. So nothing that you see here is stored unencrypted. You also get an audit log. So every operation that you're doing, it's audited. You can add and remove passwords. You can change them. You can power off the device. And when you log out, the encrypted partition will be locked again. So now I'm going to show you signal connectivity. I'm assuming that you're all familiar with what signal is. Yeah? Okay. So we have a plugin for signal here, which allows me not only to chat with other mobile phones. So in this case, I'm talking to my mobile phone. So I just received a message from my Interlock here. So hello there. But also, we can share files. So now I had a file on the encrypted partition. And of course, I could just Pgp encrypt that file. I could download that file, I could put it into my email client, and then I could send it away. But we know how that's complicated nowadays. So what I can just do, I can just send a file which is sitting on the encrypted partition of the Armory to my phone. So I just sent here a picture of my cat. And the reason why we are doing this is not only to have communication between a phone and a USB Armory and a USB Armory and a phone, but also to simplify communication between 2 different USB Armories. So for instance, my colleague Andre there has another USB Armory, which is blinking over there, much more loud than mine. Mine is better, it's a steady LED. Yours is blinky, it's distracting. And I have his number here, and what I can do, or what he can do, he can send me a file from his encrypted partition on the USB Armory, end-to-end encrypted with signal, directly landing on the encrypted partition of my USB Armory. So now I get a notification, see, I received the message, and if I go onto his contact directory, I see that a file appeared. And that file, let's download the file. Let's see what it is. And it's another picture of a lovely cat. So our 2 cats can decide to have a love story and share pictures completely securely and safely with Interlock and the USB Armory. So, and also the interesting thing is that by using the signal infrastructure, this way we can send much bigger files with what you can do on a mobile phone. There's no size limit there. And also the metadata of, let's say, the file name gets preserved, which is something that you cannot do if you just communicate with mobile phones. And this is really to make a very as efficient as quickly as possible file transfer, which in this specific case, my laptop is just acting as a router and nothing more. And all it sees is encrypted traffic. And I don't have to worry about GPG or any other things. I just use this functionality, which we think is pretty great. And of course, I can also chat with Andre if I want to. And this chat also lives on the encrypted partition. So if I want, I can also leverage on all the functionalities that we have here on the file manager to download the file and manage the file like it would be any other file on this system. And as soon as I log out, the partition is locked and encrypted again. So this is one software that we've done. It's on our GitHub repository, and again, it doesn't necessarily need to be used on a USB Armory. It can be used on pretty much on any hardware you want. So even on your laptop, if you have a container which can access an encrypted partition, and you wanna access to that, you can also use Interlock if you want. We also have an embedded Interlock distribution that leverages on all of the features that I explained to you about secure boot and the security coprocessor to have as tight as secure environment as possible running on your USB Armory. So the build-root environment that we have, so build-root is a framework which is developed by people like Atmel, but it's a completely open source and there are many sponsors to it, which allows you to easily create a final embedded image for embedded systems. And the way it works is that you have configuration files which are similar to the Linux kernel configuration, and then you just type make, and you end up with your kernel, your user space, all conveniently packed in the way you want it to be. So with the build-root environment, with just 2 commands, you can automatically create a monolithic kernel which will include all of the user space as a RAM disk inside the kernel image. And why are we doing this? Because the idea is that you have your system on a chip which secure boots the bootloader with secure boot. The bootloader with the verified boot verifies the kernel image, but the kernel image doesn't only contain the kernel, it also contains inside all of the user space application and Interlock as well. When I say all of the user space application, I mean just the standard Linux tools necessary to maybe create a microSD partition and to set up networking. Nothing fancy. We're talking about less than 4 megabytes of image, including Interlock itself. And so we maintain the root of trust in executing all of this code. And then everything else that is on the microSD card is just an encrypted partition, where your data or even programs can be there. So everything is locked down and either signed or authenticated with your credentials into this case. And our default image also, you can put it on a blank microSD card and will automatically create the encrypted partition at the first boot, and then you can also change the passphrase for that. So to make it as easy as possible. And you can optionally enable the security coprocessor, which means that every credential that you create for the encrypted partition on that device will be tied to the specific key of that specific system on a chip that you have. Okay, so these are the defensive uses that we created the Armory for in the first place, but of course there are also some offensive uses for it, and there's a lot of papers which play with the idea that not only you can emulate arbitrary USB devices with the USB Armory, which you use a lot in penetration testing of USB stacks and USB drivers. The amount of freedom that this controller gives you is a lot. So you can emulate and you can bring up fairly complex drivers and modify them so that they misbehave without losing any performance and any speed. And this is the USB Linux gadget framework that we use, which is the same one that we use also for emulating a network card. And there are a few papers around about doing USB eavesdropping attacks or doing network hijacking attacks with the USB Armory, since you can emulate an arbitrary Ethernet device from it. And recently you might have seen this attack here, which was published, where it's about stealing credential tokens from either OS X or Windows machines, even if they're locked, by just plugging a USB Armory that emulates a network interface with a higher priority and then provides authenticators that would respond to all the authentication requests from Windows. And this allows you to get the NTLM hashes from the machine, even if it's locked. So just by plugging in the armory. So it's of course something that you can do with any device which is capable of emulating USB Ethernet cards. But in this attack, in 10 seconds, the credentials were stolen. You can find a link of this in our wiki page under external contributions, and this is the blog post that Brandon did, and it's a step-by-step tutorial on how to configure the USB Armory to do this kind of operation, and what you end up with is this, which on the USB Armory in a SQLite database, you end up with the actual NTLM hash and the username, which then you can crack or can use in pass the hash attack. So this, I think this got really popular last week, and I think it's one of the best examples of using this device for offensive purposes or offensive studies. So it also makes a good platform for that. And on our own, we also found at the end of last year, and it was disclosed, I think, at March of this year, we found a bug for both OS X and iOS, where by plugging in the USB Armory and presenting a misbehaving network driver, even if the machine will be locked, we will be able to have a crash into kernel land because we would present certain descriptors that would cause memory overruns in the network buffers of the driver that would handle that on both OS X and iOS, because the driver is actually the same. So we investigated this on OS X, but surprisingly, it was also working on iOS, panicking and rebooting the machine. And this memory corruption is triggered regardless of the fact that the user is logged in or not. So it requires no user interaction. And actually, the trigger is traffic which is sent by the USB Armory to the host, which makes it very inconvenient and scriptable from the device itself. And a single IPv6 packet can be used to reproduce the issue. So now, of course, the issue has been fixed. We reported it to Apple, and we disclosed the bug only when it was fixed. And yeah, it's an interesting bug, and it's very similar to this OpenBSD issue here, where memory buffs are being overwritten. So, but regardless of this specific issue, this is just to prove the point that the USB Armory also makes a very good case for, testing USB payloads, whether it's, something at a lower level or something at a higher level where you have to present a full kernel driver. And it's very easy with the gadget framework to identify the drivers which are supported and manipulate them in a way that you would make your host misbehave. So, almost good with time. I think I also saved some of the delay that was there. So I thank you very much for your attention. I will be very happy to take questions if you have any. Thank you very much.
Questions?
Any questions? Yeah, where are you? Raise your hand.
How many layers did the PCB have due to crosstalk limitation, which probably did?
Right.
And second, did you consider or maybe even file for getting a FIPS 140 certificate in order to validate its tamper-proof capabilities?
So the first question is how many layers the board has. So the first alpha version of the board had 8 layers. And then the 2 ground layers that are usually kept to minimize crosstalk and to maintain better EMI, we removed them to see if it would work anyway. And yes, it was fine without the 2 ground layers. So, that saved the cost of the PCB by 50%, and it had no negative effect. So we started conservative, and then, we went less conservative to understand if it would work anyway. I mean, we have a lot of non-conservative violations here. I mean, if you take the recommendations from any component datasheet, there's no way you can apply all of those in such a design. So that was one of the first optimizations that we did. So we have a top and bottom layer. Then we have 2 ground layers, which, 2 are kept there, but there would have been 2 more in the inner core. And here we have the power layers, which are these 2, right in the middle. And then we have the 2 signal layers. So Sorry, actually, this design, okay, no, it shows the 2 ground layers, but those were actually not produced in the final board. Sorry, it's just that I opened the file which has all of them. So these 2 were gone, and then we just have these layers over here. The second question was if we consider to apply for FIPS certification, right? In our testing of smart cards specifically, and a lot of HSMs, we find that the FIPS certification has a very relative practical value. There are still some mistakes that you can make. And for a company of our size, and with the budget that we have for this project, it's not a process which we thought it would be worthwhile. Also, this device has been designed specifically for having no persistence whatsoever on it in terms of code. The only thing that persists is the fuse public keys and the inner secret key, which is burned by NXP. So the way we promote the use of the device is that if you lose it and somebody has it in its possession, there is no value that you can gain but actually tampering with the device. Because all of the secrets are either using the right form with something that you have, and it's not like a SIM card where, you know, the pin unlocks it, but really doesn't decrypt any contents of the SIM card. Like a SIM card or a smart card is tamper-proof because the pin is only something which sets a state which then allows you to use it. But it doesn't necessarily mean that the contents on the smart card are encrypted, which is why the tamper-proofing capabilities of the chip are very important. In this case, we have no persistence. So even if you decap the chip and you're very good with those kind of attacks, worst case scenario, you get the secret key out of it, which anyway is going to be using the right form with your own passphrase to encrypt secrets. So we wanted to minimize the importance of tamper-proofing on this device. I mean, we see a lot. We do a lot of tests on point-of-sale devices in the financial sector, and we see that if we bypass the tamper-proofing sensors, the whole security of the device falls apart because it completely relies on those mechanical sensors. So in this case, we wanted to avoid all of that, and that's why we thought this kind of certification wouldn't be interesting for us, not to mention expensive and exhaustive to do. Thank you. Any other question? No? Good. Lunch? Yes, lunch. Thank you very much.